Welcome to Rubber Duck Engineering. Tonight, we're going to add free to our simple malloc. Hi, Dr. Barth.
Hey, Eric, how are you?
I am excellent. I spent pretty much all day coding, which I haven't done in a long time, and it was excellent.
I went into the actual office and I had lunch with human beings who were
What?
in 3 dimensions, and we were having lunch at this like salad place, and I was in the salad place, and the person I was lunch with was waiting outside the front door. It took us like 15 minutes to find each other, which never happens when you meet people over like Zoom or whatever. You just dial into the same Zoom, and there you are, and
Well, sort of. So now that I'm in the outside world and I can't assume, as folks know, I left Google, I don't know, 6 weeks ago or whatever. Now I can no longer assume that everyone uses Meet.
Mhm.
And this is actually a problem because I will join things and it'll be 2 minutes after and be like, did I join the right thing? Are people using Meet? Because you never get the Meet IDs wrong inside Google because like everyone clicks on the one that was automatically added to the calendar. But like in the outside world, who knows?
Don't you just get like a Zoom link in the email and you click it and there you go?
Well, you do, but like sometimes the links have both a Meet and a Zoom. Sometimes it's their Zoom, sometimes it's your Zoom, and like it just.
Okay, that makes sense. I had attributed to like not having lunch with someone in a long time and like having lost the social skill of like saying where actually we were going to meet in this big salad confabulation.
It is a social skill. Yeah, so we could jump into the code machine. I got lots of things I could talk about too. But yeah, I think we're doing performance tonight. We're doing free, and I think we did free, but we're gonna make a real free.
We made a list in the README. Should we show the list? And
yeah, we have README listing technology. Things to do. Benchmark, slab allocation, an extra L. Oh, this thing's spell checked. Press header, free list.
Personally, I'm excited about the benchmarking. I think that's a interesting dimension to look at this problem through, or lens to look at it through, dimension to explore. I'm mixing up my metaphors.
Do we need to have do we need to do this one in order to?
No, I think we can just. So my theory on the performance, by the way, is because we're just keeping everything in memory order in our list. As we allocate, we're gonna if we allocate 3 things, we're gonna have to touch 3 things to find the 4th thing. But I think we could just write a loop that just calls the mymalloc function.
Okay. Benchmark.c.
Yeah, maybe we should just. Yeah, we may want to put main in its own file now so that we can link malloc.c and benchmark.c together.
Cool. Yeah, we're gonna. Well, what was main even doing? This was like a. It was like a
test. It was like a smoke test.
Test.c, something like that. There you go.
Okay, I'll just move it over there.
Okay. And we're gonna end up with a make file here eventually. But okay, so this thing wants to include malloc.h. I was showing somebody C today and just being reminded about how far the world has moved in the last 50 years of programming.
So turns out malloc.h is empty. So
yeah, it's fine. It's very easy.
Step 1, we need to add some.
Write the C magic. Does this work? You don't need to do the include dance anymore?
So it's non-standard, but it works. And it ends up being used a bunch in the actual standard library.
Yeah.
Because you don't really know what paths things exist at.
Well, because otherwise you have to do 3 lines of dance.
Yeah, and you end up leaking some symbols. Anyway, it works. It's non-standard, but it works.
Okay.
It's good enough for me.
Is Clang that we didn't ever wire up Clang format. Does Clang format do this or this?
It's a setting.
Okay.
I forget what the default is.
It doesn't like size T. We need.
Not standard. It would give it to me. Is it a different one? Standard def.
Oh. So I did switch us from being running Visual Studio Code in Windows using WSL to now I'm running Visual Studio Code in WSL. And that got the paths to fix. So it should do the squiggles now.
Okay, well,
I just don't always trust the squiggles.
I see. Maybe it's just slow. That's fine.
Okay. Include errors detected. Please, squiggles disabled for translation unit. Oh, I think the squiggles are just slow. It also warns you whenever you open. It's like you open this in a we're virtually mounting the NTFS into WSL. Everything's going to be slow.
Oh my gosh.
So here's our fancy header. Okay.
I think we just try it and see if it works. The compiler will tell us if we get it wrong.
Great. So now we have to figure out how the hell do you, there's like a, what's the nano sleep, or how do you do how do you get high precision timing in C? I have not done this in a long time.
Do we want it in C? We can do it in C.
Well, oh, I see. Otherwise, you were just going to time the whole thing?
Yeah.
I think you want to do it in C.
Okay, we'll do it in C. Time.
It's not nano sleep. It's I don't think I opened a here, 1 second. I'm gonna.
You want monotonic clock. You want this one. Get time monotonic.
Okay. 1 second. Let me open up a browser for the rubber ducks.
There's nothing stuff in here that seems sensible.
Okay. Yep. So we make a time spec on the stack. We fill it.
And then we should try to print this out to see what it has in it.
Oh, this reminded me of something I want to talk about. There was a thread on Hacker News this week that talked about the disease that has infested modern programming, where we just use left pad off of NPM, and that it's just better if you just write it yourself. And it was occurring to me as I was doing a bunch of coding today that Copilot is totally changing this game.
Oh, because it'll just autofill.
It's actually much easier now to build. So I went looking for a CSV parser. And I was like, whatever. None of these look right. I'll just write my own. And then I started to write my own, and Copilot just wrote it for me.
Mm-hmm.
And I think that actually might be it's going to cause a different kind of code reuse. Well, different problems, but it might result in n simpler programs. I should have checked, but here we go. I can jump to definition.
Yeah, this should give us time in nanoseconds. Yeah, nanoseconds. So we should basically print these out. Let's just take a int 128p time seconds times how many seconds in a nanoseconds. That's what Copilot thinks the answer is.
Oh, I think I may not have Copilot inside. That's a problem. Should have tested my configuration more.
Okay, and let's make a nano sleep for nanoseconds, and then do this again. Again.
I remember using man, like the man page tool, to do lookups of types to figure out what header they came from.
Oh, that's a good idea.
The way I remember doing it back in early aughts.
All right, does this build?
Well, int 128 is
That's not a thing?
Well, it may be int 128t header. You int.
All right, you want 64? Well, let's just try building it and see if it works.
All right.
I don't trust the squiggles.
I hear you.
Hey, welcome to the show.
Bench mark. Let's see.
Oh, too many L's. We went down. Okay, try now. What? Main does not return void, my friend. Main returns int.
Oh, sorry.
I mean, it doesn't actually matter, but okay. So now if we run this, yeah, what do we got? Main is an amazing function. Like, it doesn't matter how many arguments it takes. It doesn't matter what it returns. Like, nobody cares. Like, you can say it returns int. You don't have to put a return statement in it. There's like a special exception in the language. Yeah, look, that worked. Look, that 7 became a 9.
Well, it also, yeah, okay. So
that's great.
So what happened there?
We put a nanosleep right on line 16 for whatever that was, 10,000 nanoseconds. And the time changed by about 10,000. So success, great success.
Can we get we want the difference here.
You want the difference? Oh yeah.
Yeah, we want int 64t. Hey, it's auto completing. T2 minus T1. T delta.
Okay. We're benchmarking sleep. The best thing to benchmark.
And this is going to be nanoseconds?
Nanoseconds, yeah. Yeah.
Does that seem right, though?
Well, let's take out the prints, right? The print is going to take forever in nanoseconds.
True.
So, yeah, that's about...
It's an order of magnitude off what we think.
Yeah, we tried to sleep for that many nanoseconds. We slept for that many.
Maybe that's expected?
Okay, so I added 2 orders of magnitude. So now I've tried to sleep for 1,000,000 nanoseconds.
Okay.
Yeah, that worked. That's about 1,000,000.
Okay, good. Okay. So there's some amount of nanosecond noise.
I mean, nanoseconds are very, very fast. Yeah. A nanosecond is, as my father would say, a nanosecond is a grain of pepper.
I don't even know what you mean by that.
The distance light can travel in a nanosecond is about the size of a grain of pepper, like black pepper. Yeah. To just put that in your noodle.
And we measure. Yeah. And we wonder why we're hitting Moore's law.
Integrated circuits are amazing. Completely amazing.
Wow.
Now you can tell me this is not true, that I've either misremembered or my father's been lying to me my entire life. That's the way I remember it.
Where the internet can correct you.
Okay, so let's try to make it like a bunch of mallocs, right? So let's say reps. How many reps are we gonna take?
Sure, 1,000.
1,000? 1,000 reps. Size.
What is this const of which you speak? Is that a C concept?
It's a normal C++ concept. I made a concept.
I think C has changed since maybe const was there in the early aughts and I've just forgotten. Oh, cute.
That's not what I wanted, but it's a neat idea, Copilot. Thank you. Oh, this is going to have a problem where the compiler will be too smart.
It'll optimize it all the way.
It will optimize it all the way. I don't know. We're going to find out.
Look at We can do malloc benchmark. We were looking at this before the show.
It definitely won't optimize it all the way when we're calling my malloc.
I just don't know like what the.
It might optimize it all the way when we're calling the real free, because it knows that what free is what does. Okay, reps. All right, let's try this.
I'm just looking to see what other people do, but okay. We're ready to go.
Yeah, you're gonna have to compile it.
Why is it sad about these things?
It's clearly not realizing that it's really on Linux.
We gotta.
Why does C++ have no garbage collector? C++ is super low level language. A garbage collector has a significant runtime cost, and so it doesn't sort of fit with the ethos of C++. You can certainly write a garbage collector in C++, but we're just doing C. There's no C++ here.
Okay, so we're segmented. We're segment faulting.
Okay.
So I don't know whether these both get linked in. I think they do if you just pass them.
Mm-hmm. Yeah. You want to pass -G and run it in the debugger to see what's going
on.
Yeah, so then instead of running a.out, yeah, run LDB. Oh, fancy.
I just don't even know. We're like way. Okay.
Oh, we're freeing we're being called free with a 0 pointer. That's supposed to be allowed. Did we not handle that case? Oh, yeah, we totally don't handle the case where the pointer is 0. This is like a legit bug.
But why are we?
Our malloc is failing, right? We're filling up our buffer. We only allocated 10 megabytes of
yeah.
Cool. Oh, we also need to init our heap, which we'll have to solve at some point. But we'll do that for now.
Okay. Yeah, our malloc does not auto init. Oh my! This is so dusty. Like running GDB LDB raw on the command line. Okay.
Okay. So let's increase the pool size. I'm just going to increase the pool size by a factor of 1 million.
Okay. So we can do more reps.
Just so we don't ever run out of space. You want to do more reps? Yeah. Okay. So now let's do 3,000.
I think the interesting thing is when you start to compare it to real malloc. Okay. You overflowed.
I made it too much.
Segmentation fault.
Gigabytes ought to be enough for anybody.
Grains of pepper are picoseconds. A nanosecond is 30 centimeters.
Oh. Did you predict it?
Grace Hopper.
Yes, you're right. I misremembered what my father told me. It's picoseconds are grains of pepper. A nanosecond, 30 centimeters. That sounds about right.
Light is really fast. Okay.
Light is super fast. Picoseconds are really fast.
That is too big for size T. This would be kilobyte. This would be megabyte. This would be gigabyte. Why is that too big?
This is not too big for size T. We just have to actually make it size T. Start with.
Oh.
There we go. Try that.
I see. It's because it's converting right at the end.
Yeah. But so what I want to do is can we do like a graph or like a chart? I just want to show that we have an n-squared problem. Like our performance is n-squared. So I want to do like 1 rep, 10 reps, 100 reps.
We have to clear the heap or something then?
Well, we run the new program each time. Like.
Oh, I see. I mean, sure, we can, using the power of, I don't think this one is logged into. I don't have a good graph without. Well, hold on. I can using I can get us a new.
I think he's being wise and not typing his password live on the internet. My interpretation of what's going on.
I'm also just moving to a browser window that is my account rather than the.
Yeah, great. So let's start graphing things.
Okay.
So let's maybe start with 100 reps and go from there.
Sure.
Okay.
I mean, if we taught this thing how to, well, that's fine. You know, we could also read it from ArcV, but yeah.
Do you want to read it from ArcV? Let's read it from ArcV.
And we come back to main being a magical symbol.
It is amazing.
I mean, it turns out main is not like a function. It just produces a symbol that the linker just goes and finds and grabs and happens to set up the stack for.
argc comes first, right? Or does argv come first?
I don't remember.
I can't remember these things.
argv, argc.
argc comes first.
argc.
Okay, that's the same. Okay, so reps is we're going to make it argv1 8i.
Oh, and we don't, is A2I provided by the standard library?
Oh yeah.
Oh, when I worked on WebKit, I think we had a different A2I that we linked in for some reason.
The reason you did that is because the standard library provided A to I is locale dependent.
Oh my god!
It'll give you different parsing. Like, you know how in Europe they have like they use dots instead of commas and commas instead of dots.
Yep.
Yeah, A to I knows that, and if you set your locale in certain places, you'll get different parsing.
We also just browsers end up doing this because every time you find yourself depending on the system, you end up being sad.
Because the system was designed for someone else for a different purpose.
Do different things. Sorry.
Okay, so this should work. So let's try running 100 reps on the command line and see if it still gets a similar number. Oh, okay, fine. What did I do wrong? Oh, not enough stars. Try that.
Yeah.
More stars. Implicit. Oh, A-I is in some header. We need to include
locale.h or something.
It's in stdlib. No, it doesn't tell you that it's locale dependent. You just have to know with your vast knowledge of works of operating systems.
Man, there's like a way to do man searches.
I included it.
I don't really get into this, but like, there's a way to search with like man A2I. Yeah, here you go. This is how I used to figure these things out eons ago. It also works when you're on a plane, by the way. All right, so that's that.
These numbers are growing very fast.
Mm-hmm.
This is what N-squared is like. At some point, you just hit this wall, and like. So just to be, I know you know, Eric, but just for the audience, just to be clear why this is N-squared, right? So from last episode, we had a linked list of all of the allocations in the heap, and to find a free space, we walk the list starting at the beginning. And so if it has 10,000 things, to allocate the 10,000th one, it's got to go visit 9,999 things and then find the free one at the end. You should just give up.
Nanoseconds is -9. 1, 2, 3, 4, 5, 6. So this is 0.2 seconds.
Yeah.
So this is 0.2 seconds, and this one, in a linear fashion, would be 2 seconds. But we're clearly beyond 2 seconds.
We're beyond. I think just kill it. Like, forget it.
Do you need this graph to see it, or
no? I think we made the point. The point is, it gets super duper slow. But I think we add a free list. it'll become ridiculously faster.
If we, just for giggles, if we moved from
to real Malloc,
real Malloc,
nothing, super fast.
Okay. So we proved our Malloc is slow.
It's epically n-squared slow. It will destroy your computer if you attempted to use it.
Okay. So now we're going back to this Malloc.c.
Right. So I think if we go back to line like 23. So I think we keep track of like next free. Probably this is going to be redundant with this is free pool, but let's not worry about that for now. And then in the pool, we'll have a start, we'll have a first, and we'll have a first free. Okay. When we initialize, when we hit the heap.
What? I'm confused. Why does the node have the next free?
Why does the node have the next free? Well, there's going to be more than one free block in general in the heap. So where do you want to?
Well, I'm just
how
like.
Do you want to keep track of it?
All right. I assume we were using the same node structure for two separate lists.
Mm-hmm.
One was the allocated list, and one was the free list.
Mm-hmm.
We move things in between. Is that what we're doing here? Then why do we need two next pointers? Why don't we just reuse this one?
So currently the next and free pointers are just a linked list in memory order.
Mm-hmm.
And so if you suppose we had two separate lists in memory order, the allocated list and the free list. When you allocated something, how would you find the location in the allocated list to insert it?
We're back to n squared again.
Yeah. So there's a way of doing malloc where you only have the free list. The other thing we can do is when the list is free, we can actually store it in the body, not in the header.
Help me understand what are these? Oh, I see. So this points to the next node, the next block in memory order. This points to the previous. What is next pre? This points to the next one that is not allocated,
but not necessarily in memory order. Just in another free one. Like if this one was free, it would point to. Think of the free ones as being a stack. So when we want to look for a free one, we're going to take the first free one from here. We're going to check that one.
Mm-hmm.
Let's assume that we can use it. Then we're going to. Then we'll take. Yeah. Basically, we'll keep a singly linked list of the free blocks in arbitrary order, and use that as sort of a stack.
So when we free something, we make it the top of the free list.
Yep, we just push it on the top of the free list. And then when we allocate something, we find the first thing in the free list that's going to work for us.
Okay. Okay, so the free list is a list on top of these. It's a, as you said, not in memory order, unrelated data structure to the memory order one, mm-hmm. where you only have where it's only singly linked.
Mm-hmm. So let's be slightly fancier. Let's put this in a different struct, which is body.
And now we see that we could easily, because now we're requiring a minimum malloc size, thus we could easily steal from the size pointer or from the size.
Well, if we have a tiny fragment that's smaller than one pointer, we'll just won't put it in the free list. We'll get it back later when we defragment, when we free like nearby stuff.
We'll get it back later when we free nearby stuff.
Yeah, like a little diagram here in like a comic.
I was worried before that if our size accounting ever gets wrong.
If size accounting ever gets wrong, we're gonna get heap corruption and the world ends.
Well, is size even needed if next is actually in memory order?
No, definitely not. So do you want to do that? We could do that refactoring. Do you want to do that one?
I think we should. I think we should. Like, I don't think we're optimizing for space. We're optimizing for like correctness and speed at this point in time.
Yeah. So like one of the items we have in the README is to compress this header.
Sure.
So this header will basically compress down to something very tiny because of tricks like that of like saying, oh,
sure, we can get rid of size.
We can get rid of the size because just like if you know where the next one is, that's we're done with it. Also, you don't need full pointers here. You just need to know like how many to go up or down. Like it's like, and sometimes instead of getting rid of size, I would actually get rid of next. And then I would say, well, we don't need 64 bits.
Sure.
Well, we can compress anyway.
Yep, makes sense.
But I think that's a separate optimization for doing a free list.
Yep.
Is there always a next? No, the last block doesn't have a next. Like when you initialize the heap, for example, you just have one giant node that is the entire heap, and it doesn't have a next because it's the last one.
Okay.
But yeah.
All right. So I think I understand where you're going now.
Okay. So let's attempt it. So let's set, when we initialize, we'll set gpool first free to equal first because it's free.
Okay.
And we'll set firsts. We need to initialize its body. So we need a function that's like struct body pointer get body node. Okay. Get body next free is null.
You mean how do you wait a second? How do you infer size of the last one? The only time you ever have a next is null is the last in the chain.
Yeah,
so you can infer size to the end of your page or whatever.
Yeah, William is raising a good point. Like you have to solve that problem. That's why instead of using next, I think it's better to keep size.
Yep.
But then you have to know when to stop, I guess. But you also have your pool, like you know how big the pool is.
Yeah, we're into the level of code where we optimize for these kind of things. In most code, you don't. Most code you don't write in C to begin with.
Okay, so I think we've initialized correctly. Yeah, the header compression is interesting, but I think I don't want to get too distracted by it. So malloc never needs to care. Oh no, we'll change malloc to go searching the free list instead of searching. So instead of starting from first,
first free.
Yeah, so let's write another function called static struct get next free, starting from a node.
Yep.
Okay. So, pilot.
Yep.
Okay, so we're going to start from first free. Where is not null. If so, the invariant. So now we should basically be able to assert that current is free. Otherwise, we've done something horribly wrong. But we're going to end up not needing that bit in a second. Okay, if current size is greater than size.
It's going to have interesting reuse properties.
What happened here? So if the current size is greater than the size, great, we're going to allocate it. I see, split the node, blah, blah, blah. Okay, and we're going to need to remove it from the free list.
This is going to be wrong.
Yeah, so let's see. We're going to have to keep track of the previous as we go through here.
this previous free?
Previous free, yeah. Okay. Yeah. Well, I mean, we could do this. How fancy do you want to be? Well, let's be slightly fancy.
Okay.
We may let's not be fancy. Okay, we could just remember where we're supposed to store the free pointer, but that's fine. Okay. So what do? We split the node.
Mm-hmm.
Okay. And so here, the new node, we need to get body set next free equal to the current get body of current gets next free. And then we need to say if there was a previous thing, then we need to set previous body previous free, its next free is new node. Otherwise, gpools next free is new node.
This is get next free current. And this you want to be set next.
Yep.
I just think I like.
No, I completely agree with you.
I like the functions.
You got to start making these functions, otherwise your life gets totally.
You're in really sad Panda land with. Let's see here. And so this is here again. Oh, this is not actually. Gpool first is not. Oh no, it is.
Okay.
So it's possible that like set next free, you want this to be to assert that next free is not ever null, but I think that's fine. Okay. This is the kind of code where you need to just litter it with asserts.
It's also set next free, right?
Mm-hmm. Right. Yep.
Okay. So I think that's fine. So we don't split the node. What happens? We need to do a similar thing. We need to basically update the free list.
Hold on. Why are we? I see. This is where we're inserting it into the list, whereas this is where it's becoming the. Otherwise, this is the case where we're the first one.
There's one subtlety here. Next free node.
I'm going to flip these. This is the. Oh, sorry. I undid.
So the I'll let you finish writing the comment, then I'll bring up the subtlety. Yeah, heat maps, Max, exactly. William was talking about heat maxes, right? Okay. So the subtlety here is we only want to split the node if there's enough left to fit the body.
We split the node. If there's enough left, yes.
So we'll say plus.
Oh yeah, we had this last time. I thought we.
Yeah, but now we only when there's something.
Oh yeah.
Yeah, so we won't bother to add this thing to the free list if it can't even.
Let's make this minimum node size then.
Mm-hmm.
Is this minimum node size?
Well, it's the minimum free node size.
Okay, well, let's still name it that. Okay. This, by the way, I'm realizing as I do it, I remember there was a point in my career relatively early on as I was learning WebKit, and WebKit was at that time a port of KHTML
Mhm.
that had been like quickly ported and hadn't been like fully cleaned up, and like I spent so many months just commenting the WebKit code.
Like understanding what it is and then writing down your knowledge so that the next person could understand it after you.
It was actually much more selfish than that. It was just like a way of me, if I could write a comment that explained what it did, it meant I understood what it did.
Mhm.
And I just found so many bugs that way. And anyways,
And also just think of like naming things is also like that, like giving them long descriptive names. But okay, this is like, why is this important? This is important because it's the minimum node size.
mhm.
So let's write that. I think it's a really good idea. So we can say const size
Minimum free node size.
minimum free node size.
What do we do when they're not?
It's fine. We just leave it. When this basically it ends up being fragmentation in the heap. So it'll be storage that's when you, let's say you allocated 53 bytes, there'll be 4 more bytes left over after that don't get used but get reclaimed when you free those 54 bytes. It's sort of a reason why realloc exists. Remember we talked about last episode where the heap can look internally and say, oh, you asked for 53 bytes. I actually gave you a slot that can hold 64 bytes. So when you realloc to 55 bytes, I don't need to move you around. I can just say, no problem. That space now belongs to you. So a lot of heap implementations will keep this as a metric. You can say heap, how much space is, how many bytes are being taken up by the heap that haven't been given out to clients. And they'll give you a report of, oh, I'm using this many for metadata. I'm using this much from fragmentation. I'm using this much for like whatever. We're not keeping all those metrics, but we could.
Yeah, there's still a bunch of other things like this can be like insert after and
yeah, this code is not pretty, and we could do like I think it might be an interesting episode to do just like taking this ugly code and refactoring it to just like how do you take ugly code and refactor to make it beautiful.
yeah, you just make it so you can understand it.
But it's like this, by just breaking out these functions that do logical things, and you could like look at them and test them and be like, oh, okay, this stanza, it's inserts after. It's mixed. So it sort of raises the semantic level of what you're doing. When you read it, you don't have to like chase the pointers and reconstruct in your mind what the linked list is. You can think of the logical operation of insert after.
This is current new node.
Well, this is really split, right?
I was just going to take these two.
Oh, just that piece. Yeah, that piece is insert after. Yeah, absolutely.
And we can further refactor it, but I would just like, I suspect we do that in other places. Okay, this is now, this is before.
We do these refactors. It's really useful to have tests because it's easy to mess up this kind of thing, right?
Oh, it totally is. I did it wrong. What is this? This is taking the. We wrote this code last week. This is why you write readable code, folks. All right, current. Make the new node's previous current. Current is before. And
I think after is better than next because next repeats itself. Like next is a confusing name.
Yeah. That's fine. I was worried about the insert after then being. Yeah. Anyways, that's fine.
You can just say left and right, first and second.
Sure. Sure. So then this is left. This is right.
But why didn't we have to update? We have to update something about left next. Like we're missing left next previous equals right.
So maybe we either missed that in the previous thing.
It was here.
It's right here.
Yeah.
We don't replace the new node in between. Yeah. Okay, good. Well, that's okay.
Right. So logically, these sides operations belong together, right?
Mm-hmm. Okay.
Okay. So should we look at the free implementation?
Yeah, I took us off track. The free implementation. Oh, I see. Now that we kept our free pointer. Okay. Yep. Mm-hmm.
Mm-hmm. So if we merge into any of these nodes, then we don't need to manipulate the free list. It's only if we did neither of these things. Let's see. If the previous node is free, then we'll merge into the previous node. Fine. Then the previous node is already in the free list. Everything is good.
Well, don't we need to update the previous node's next free?
No, because we didn't. This new node that we created is gone from time. Like it's.
I see. It never had a next free.
Yeah, okay. It disappears from the universe. Right, okay. Okay. Right. Okay. If the next node is free, then we're going to destroy the next node, which is a problem in this world because we don't know, because the free list is singly linked. We can't go fix up the whoever was pointing to this next node.
Mm-hmm.
That's okay. We don't need to do this coalescing. So we could take this out.
And just leave fragments again in the heap?
So we could leave, yeah. So then that would fragment the heap. So it would be like adjacent free areas that we didn't know how to merge back together that then couldn't have a big allocation spanning it. Or we could make the free list doubly linked, in which case we could fix things up.
Just comment it out for now.
Okay, so let's leave a comment about this. To do, we merge with the next if it's free, comma, but we don't know how to maintain the free list. In that case, we need the free list linked, and we could update it. We could do it. Okay. I'm just going to delete this. It's in Git history if we ever want it back.
Okay.
If we didn't merge, then we need to update the free list. So the easy way to update the free list is exactly what Copilot did.
Mm-hmm. Yep. I need to do this.
Yeah, you're going to break that into a non-ridiculous function.
It's like struct node pointer, right? Node from pointer.
Yep.
Void star.
Yep.
Now we need pointer from node.
Mm-hmm. The nice thing about doing it this way, just to pile on to Eric's refactoring, which I dearly love, is having these two functions next to each other means you can stare at them together. Whereas if they're just written in line in your code, wherever they happen to be, then they're likely to be farther apart from each other.
You just get it wrong. Okay, and then we're gonna do node from PTR. I see. This
So
is the
we
only-
are doing something not quite ideal, which is we're refactoring and changing the semantics at the same
We
time.
are.
Like if Eric sent me this patch, I would say, I love all your refactorings. Can you do it in a separate patch from adding the free list? But
Amen.
this is a YouTube show. This is not a code review.
I even do that in my own local coding, by the way. When I've like done too much in a patch, I'll like split it out. I don't actually ever go back and look at the history, but it just, I don't know. Too many
I
years.
often do this. Well, I'll save the commit, and then what I'll do is I'll use the thing that lets you like add individual diffs
Yep.
to like make a new commit out of some old commit, and then I make sure that like by the end the diff that I have is empty, meaning I found a home for all of the changes I wanted to make in different.
What is this?
Different CLs.
Current. What is this? Carestar current.
This is split node at where the
No,
at is.
what is this? This is this is a. Right, so that's not. It's not. Is it trying to? It's trying to get a pointer.
No, it's materializing a new node by splitting a node. So it's a good function to break out. So basically, you input a node, you input a size, and it returns to you a new node that is that size over.
But there's we also do pointer from node.
That's right at the end of malloc. It's right here. It's on line 139.
I see. This is. I see. Current. This is. Oh, oops! I can't squat on that name. It's a little weird that we is C normally lowercase names for structs?
I don't know. The C doesn't really have a style like this is.
We just collided with our nice local variable line return. Okay. Have we broken all the things now?
I don't know. Should we try it? Like I don't know whether it works anymore.
Okay. So let's try.
Oh, okay. Or was our cert? Not like a line 99. Just add a cert.h. Try it again.
I could see it, but yes, I assumed you did that. Yeah.
Uh-huh.
Okay.
More zeros. Yeah. It's not n squared anymore.
It should always be hitting the first thing in the free list because we're not varying the malloc sizes.
Yeah.
We're getting
Exactly.
any sort
Like
of pathological.
we could give a much harder benchmark than this. Off topic. I remember Eric saying that game engines have large engine code separation. Is there any game engine that does it correctly? I'm curious about your opinion on Bevy and Theater.js.
So they have as much engine code separation as browsers do, because as a game engine user, you get to write in a different language than the game engine itself is written in. Bevy may be different. Bevy is the Rust game engine.
I see. And do you program it in Rust? Like when you write your game, you write in Rust?
I think so. So it's possible that Bevy sort of does this for you. I have not tried with Bevy. I actually follow it on Twitter, and I get to see all the fancy games being made with it. My from the hip guess is that Bevy will have difficulty adoption. This is totally hot take here, due to being
throwing Bevy under the bus a lot.
Yeah, no, I mean, I should go look at it. But I love Rust, but I have personal beef that it just has a learning cliff, and it's just more difficult to write in than like your average Node.js developer, I think, is going to be happy with.
I think, by the way, that this is something that Rust advocates don't realize because they've already climbed over the cliff and they're like, wow, it's beautiful up here. Like, look at the great views I have.
Yeah.
And they forget about like, oh, it actually like takes something.
If I can take us on yet another tangent, I want to get back to the rest of N's question and Bill's.
Oh, sorry.
This is something
back
this
to
is the importance of going and talking to customers. Like, I know it's really hard for us antisocial introverted engineers, or at least some of us like me are antisocial introverted engineers. But you go and you talk to customers, and the problem you think they have, they don't have. Instead, they have the like most amazing problem that you could like. I spoke to someone today, and they were talking about how they had 40-minute build times.
Something has gone horribly wrong. I don't care what your system is. If it takes 40 minutes to build, we build an entire operating system in a few minutes.
Yeah, like, something had clearly gone horribly wrong somewhere, but like the fact that they were living in that reality because I, the person who had provided them the software, had not like made it obvious, what had gone wrong, or I hadn't fixed the edge case that they were hitting, right? Like, so like, I think that it's really helpful for us to get out of our, coding seats and go talk to our users and realize that they actually have way simpler problems than we think they do.
Like this n squared thing. Like the reason it's sort of fun to bring it up, but like literally we spent a lot of time optimizing WebKit, just finding n squareds and taking them out.
Yeah.
And like everything gets faster. Like even for n of 10, n squared is 100. If you reduce it to n, then it's just 10. It's 10 times faster.
Yep.
And 100 is not a big number.
Yep. Your test case never added 1,000 attributes to the HTML tag, and realized that then, every time you are down in some attribute, you crawl up and look at the like cascading, whatever. But like your test case had 2. Mm-hmm. Anyways, Theater.js I've not tried. I should. I didn't know it existed. I should go look it up. But anyway, sorry. William had asked a question.
Gnarly Git histories. So having like a code review process really helps with this, because when someone sends me a gnarly contorted thing, I just say, "Can you make this pretty? I can't even review this, please." Like it obviously depends what you're doing. Like if you're trying to like move fast and break things and like you're sort of in the early stage of a project, fine, this is exactly what you should be doing. But like if you have a team of, let's say even 10 people, then like maintaining a good history that someone who didn't work on that part can go back and see is important. But like I agree. So I read some one of these like famous Linus Torvalds emails where he was explaining the like theory, the like idea behind Git, and the idea behind, at least that I remember from his email, because I remember my father's advice incorrectly, so I probably remember this email incorrectly. But what he was saying is that these sort of gnarly contorted histories are great for your private history. Mm-hmm. But when you send him a patch to Linux kernel, that's a public history. And so it should be formatted in a way that's optimized for people reading and understanding it.
Yeah.
So I think, and then he also had the idea like once something is public, it's frozen in its Git hash is now incorporated into everything in the universe. And so it can't really be changed. So I think I wouldn't go clean up things that are already public.
But I think that makes sense for the Linux kernel. I don't think it matters for your local repo.
It kind of matters because like let's say somebody forks it on GitHub, right?
Sure.
And having them update their fork, if you go rewrite history and change all these public hashes, sure, it like messes them up.
Oh, so, I don't mean the rewriting history. I just meant the having a beautiful, Git. Like it matters a lot for the Linux kernel and Chromium and all these like that like every commit is nice and followable as much as possible. I was thinking in this related vein, if I can take us on a slight tangent today, I signed a CLA today for trying to send a patch, and then the bot yelled at me. Another bot that the individuals had yelled at me, not about the CLA, which I already signed, but about that the title of my thing was not quite right or something like that. And it just sort of reminded me of the practice of like barriers to entry, like groups of individuals, sometimes intentionally, sometimes unintentionally, sort of like put up walls to keep the outsiders at bay or whatever. And that's not what these individuals were trying to do.
But it's sort of the net effect, right? It ends up being this tribal knowledge of how to format your patch correctly.
And I think it's an interesting problem in open source because you both want this kind of thing for as you move a team from 2 people to 20 people, you have to do these kinds of things to like help have the culture and have the standards and whatnot. but it also then makes barriers for outsiders trying to like come and be part of your club, which is like there's competing incentives in open source.
You know, when I had to send a patch to the Linux kernel, like literally I had to install Linux on a computer in order to run a mail client that could format a mail properly that the Linux kernel community would accept to contain a patch, which is fine. Like that's their super successful project, and that's what they wanted me to do. Like I was becoming indoctrinated into their culture, and I learned how Mutt worked because that was the only way I could properly format an email. But honestly, I think this is one of the things I think is really great about GitHub is it made such a repeatable pattern for sending people pull requests, like because there's like a default way of doing it, and you can't even like turn it off in your project. Like you have to allow people to send you pull requests. You can ignore them, but you can't stop them from coming.
I think you can now. You can archive, but yes,
that feature I think must have come way later. After GitHub has already
10 years into their existence
become the thing.
This was also part of like we made a conscious decision to do Flutter on GitHub. I believe that came from you, and it in effect lowers the barrier to entry because all of these things, all these paper cuts. You know, if you think you might have 10,000 people try and send you a pull request. By not being on GitHub, you just cut that number to 10, you know, or to 100. Or by having a CLA bot, you cut it to 1,000 instead of 10,000.
Well, it all came from the scar of working on a web browser and that being just a separate community from people who make websites. And so what I really wanted to do is I wanted the people who worked on Flutter to be the same people, the same tribe as the people using Flutter to build apps, because I thought that was really important. I don't know whether we got closer. I probably didn't succeed at that, but that's what I wanted. That's why I was making those choices.
Oh. So we've used our hour. Did we tie a bow enough on where we were with Malik?
Yeah, I think it's great. We made it like a bajillion times faster because we got rid of the n squared. How many bajillion times faster? I don't know. Like how many zeros do you type at the command line?
Well, it's now possible to do 10,000 objects, or whatever it was, 10,000, 100,000. Well, it was now possible to do 100,000.
So. Great success.
Anyways, this was fantastic as always. Thank you all for coming by. So many interesting questions and comments tonight. And to all of you who are watching this tomorrow, I hope you're having a wonderful day, and we'll see you all next week.
Yeah, see you next week.